purpose of this videotape is to explain the quantum numbers. This will enable you to better understand the periodic table. An understanding of the quantum numbers will help explain why the periodic table is in groups of 2, 6, 10, and 14. It will also help explain the chemical activity, since activity is based on paired and unpaired outermost electrons, along with filled and unfilled orbitals of lower principal quantum numbers. The motion of the electrons about the nucleus may be described by 4 quantum numbers. This videotape will describe and discuss these numbers. The 4 quantum numbers are called N, L, M, and S quantum numbers. We will discuss each of these quantum numbers. N is the principal quantum number. The limits of N are 1 through infinity. However, for practical purposes, it is 1 through 7, which corresponds to the 7 rows on the periodic table. The N quantum number determines the size of the electron cloud. If the radius of the first energy level would be approximately this size, then the second would be this size, and the third would be this size. These electron clouds may be called atomic orbitals. Sometimes these are called K, L, M, N, O, P, Q shells and are illustrated in this manner. The second quantum number, L, is known as the azimuthal quantum number. It is sometimes called the subsidiary or orbital quantum number. The limits of L are from 0 to n minus 1. Shown here, if n is equal to 1, then L is equal to 0. If n is equal to 2, then L can be 0 or 1. If n is 3, L may be 0, 1, or 2. If n is 4, L may be 0, 1, 2, or 3, and so on. Azimuthal quantum number determines the shape of the electron cloud. If L is equal to 0, the cloud is said to be spherical and is the S sublevel. Here is a pictorial illustration of the S sublevel. If L is equal to 1, it is called a dumbbell. It is referred to as the P sublevel. Here is a graphic illustration of the P sublevel. If L is equal to 2, the shape is an elongated dumbbell and referred to as the D sublevel. Here, too, is a graphic illustration of the D sublevels. These orbitals are sandwiched between the P orbitals. M, or M sub s, is the third quantum number. It is called the magnetic quantum number. It designates the orientation of the electron cloud in space and also determines the number of places that electron clouds may be placed. An example, when L is equal to 1, M may be minus 1, 0, and plus 1. This means that minus 1 may be this lobe, 0 may be this lobe, and 1 may be this lobe. The limits of M are from minus L through plus L. Shown here are the values of M. If n is 1, L is 0, and M is 0. If n is 2, then L can be 0, and M would be 0. If n is 2, and L is 1, then M can be minus 1, 0, and plus 1. If n is 3, then L can be 0, then M is 0. Again, if n is 3, L can be 1, then M would be minus 1, 0, and plus 1. If n is 3, L can also be 2. If L is 2, then M can be minus 2, minus 1, 0, plus 1, and plus 2. The fourth quantum number is known as the spin quantum number. It is known as S. This S is different than the S sublevel. S designates the direction of the spin of the electron about its own axis as the electrons move about the nucleus. The spin is either clockwise or counterclockwise and is given by plus or minus 1/2. These are the 4 quantum numbers. Two rules must be followed when you assign quantum numbers. These are Hund's rule. The electrons enter each orbital of a given type singly and with identical spins before any pairing of electrons of opposite spins occurs within these orbitals. The second is Pauli's exclusion principle. In any one atom, no 2 electrons have identical sets of quantum numbers. Now let us look at the periodic table and assign quantum numbers to some of the elements. The quantum numbers of hydrogen are 1, 0, 0 plus 1/2. This means the first electron goes into the first energy state in this S sublevel and with a clockwise spin. Helium's quantum numbers are 1, 0, 0 minus 1/2. The second electron of helium goes into the same energy level as the electron of hydrogen, but with a counterclockwise spin. Quantum numbers of lithium are 2, 0, 0 plus 1/2. It is similar to hydrogen, except the electron goes into the second energy state in this S sublevel. The quantum numbers of beryllium are 2, 0, 0 minus 1/2. And it is similar to helium, except its electron enters this S sublevel. Boron's quantum numbers are 2, 1, minus 1 plus 1/2. You will notice it enters the second energy level, but it goes into this p orbital, and its electron has a clockwise spin. The quantum numbers of carbon are 2, 1, 0 plus 1/2. And its electron also enters the second energy level in this p orbital, and it has a clockwise spin. Nitrogen's quantum numbers are 2, 1, 1 plus 1/2. Its electron enters the second energy level in this p orbital, and it too spins clockwise. Oxygen's quantum numbers are 2, 1, minus 1, minus 1/2. You will notice the spin number is minus 1/2. Therefore, it will spin counterclockwise. It will enter one of the p orbitals and pair one of the unpaired electrons. Fluorine's quantum numbers are 2, 1, 0 minus 1/2. This electron is similar to the one added by oxygen and will pair another unpaired electron in the p orbitals. Neon's quantum numbers are 2, 1, 1 minus 1/2. This electron enters the second energy level, spinning counterclockwise and pairing the last unpaired electron in the p orbital. In order to be consistent, we have arbitrarily assigned the m quantum number from the lowest to the highest value. Therefore, when L is equal to 1, the m will be minus 1, 0, and 1. And in your math classes, you may call them the x, y, and z axes. Let us look at the quantum numbers in row 3. Sodium quantum numbers are 3, 0, 0 plus 1/2. Magnesium's quantum numbers 3, 0, 0 minus 1/2. Aluminum 3, 1 minus 1 plus 1/2. Silicon 3, 1, 0 plus 1/2. Phosphorus 3, 1, 1 plus 1/2. Sulfur is 3, 1 minus 1. The spin is minus 1/2. Chlorine is 3, 1, 0 minus 1/2. Argon is 3, 1, 1 minus 1/2. The first electron after argon should go in as follows: 3, 2, minus 2 plus 1/2. However, the electron will be 400 plus 1/2. In order for the electrons to be pulled down into the third energy level, more attraction is needed from the nucleus to overcome the repulsion of the electrons. Therefore, the first two electrons that would be in the third row with an L number of 2 are repelled and remain in the fourth energy level. After 3 protons are added to the nucleus, there is enough attracting force to pull the electron into the L number 2 level. This happens every time you complete the group with L equal 1. You will notice it ends with one of the inert gases. Let's take a look at the shape of the orbital with L quantum number equal to 2. These are called the d orbitals. Notice that the electron cloud density is very high. This accounts for the filling of L is equal to 0 in the next higher energy level before L equal 2 is filled. You will notice the principal quantum number of the B, or the transition elements, is one less than the row in which they are in sequence. SC starts 3. Quantum numbers of vanadium are 3, 2, 0, plus 1/2. Quantum numbers of zinc are 3, 2, 2, minus 1/2. The rare earth elements all have L is equal to 3. Their electron density is so high that additional electrons are repelled until electrons have been added to 2 higher energy levels. Therefore, the principal quantum number of the rare earth elements are 2 behind the row in which they are located. The first element in row 6 has a principal quantum number of 6. The B group in this row has a principal quantum number of 5. And the rare earth element in row 6 has a principal quantum number of 4. The A groups following the rare earth elements in row 6 have a principal quantum number of 6. Let's review what we have covered on this videotape. The principal quantum number of all the A groups correspond to the row in which it falls on the periodic table. Here are the A groups, and these are the rows. Therefore, the principal quantum number of this row is 1, this row is 2, this row is 3, and so on. In reviewing the L numbers with the periodic table, we can make this summary. When L is equal to 0, the elements fall in groups 1A or 2A. Helium is unique and should be placed at the top of 2A. In many periodic tables, it is placed on the top of both 2A and 8A, since it has properties similar to both. When L is equal to 1, the elements fall in groups 3A through 8A respectively. When L is equal to 2, the elements are called the transition or the B groups. When L is equal to 3, the elements are called the rare earth series. Summarizing quickly, when L is equal to 0, it's called the S sublevel. The elements will be found on the periodic table in these columns. When L is equal to 1, the P sublevels on these columns. And when L is equal to 2, the D sublevels found in these columns. When L is equal to 3, the F sublevels are the rare earth elements. M determines the number of electrons that can be placed in a sublevel. And examples, when L is equal to 2, then M can be -2, -1, 0, 1, or 2, giving 5 places to place electrons. Here is an example of the 5 d orbitals. If a single electron is placed in each one, and then each one is paired, you can have 10 electrons in an atom where L is equal to 2. And M may be -2, -1, 0, 1, and 2. And this is a composite of the 5d suborbitals. This explains why the periodic table has groups of elements of 2, 6, 10, and 14. Our modern periodic table, L is 0 through 3. The S quantum number designates the spin, either clockwise or counterclockwise. These elements would have a clockwise spin and be unpaired. If there is more than one space available in a given suborbital, for example, when L is equal to 1, then M can be minus 1, 0, and 1, accounting for 3 available spaces for electrons. The first 3 electrons would enter as unpaired electrons and all spin in a clockwise manner. 1 would spin in each of the separate orbitals. 1 in the p sub x orbital, 1 in the p sub y orbital, 1 in the p sub z orbital. The next 3 electrons would enter and pair the single electrons spinning in a counterclockwise motion. Phosphorus would have 3 unpaired electrons. Oxygen would have 2 unpaired electrons. And fluorine would have 1 unpaired electrons. Neon would have no unpaired electrons. Since we have completed our introduction of the quantum numbers, let's go to the periodic table and assign some quantum numbers. Barium is element number 56. It is in row 6 in group 2A. Therefore, the principal quantum number is 6, the L number is 0, and the M number is 0. The S number is minus 1/2, which means it spins counterclockwise. Another example is gold, element number 79. Since AU is in row 6, however, located in the B group of elements, its principal quantum number is 1 less than the row it is in, making it N equal 5. The L number is 2, and the M number is 1. The spin is counterclockwise because it is located in the last half of the transition elements. Lead, element number 82, is also in the 6th row and in group 4A. The principal quantum number is 6. The L number is 1, the M number is 0, and the spin is clockwise, or plus 1/2, because it is in the first half of the p orbitals. An understanding of the quantum numbers helps explain the structure of the periodic table. If you learn how to use a modern periodic table, you will be able to do well in your study of the physical sciences. Question number 1. What letters represent the 4 quantum numbers? Question number 2. If the electron is in a p orbital, what is its L number? Question number 3. If the last electron has a plus 1/2 spin, is it a paired or unpaired electron? Question number 4. What is the principal quantum number of the transition elements in row 5? Question number 5. Where do you find the elements with L is equal to 3 on the periodic table? Question number 6. When L is equal to 0, what is the shape of the electron cloud? Question number 7. How many d orbitals are present in the 4th energy level? Question number 8. What is the element with the quantum numbers of 3, 0, 0, plus 1/2? Question number 9. What is the quantum numbers for the element number 35? In question number 10, what is the quantum numbers for the element number 47?